general relativity, step by step. We've got this nice equation here or this nice expression here for the metric tensor in the vicinity of a central gravitating object, and we've pinned everything down except for this c, which appears here and here in the metric tensor. So how are we going to find that? Well, you'll remember when we specified, or when we set out the Einstein field equations, there was an uncertain parameter in that, there was an uncertain constant in that, and we evaluated that constant. We found out what that constant was by comparing the predictions of relativistic formulas, with the predictions of Newtonian theory, and applying the relativistic formulas in the weak field limit. And we're going to do just the same thing here. Okay, so I'm going to consider the geodesic equations again. Geodesic equations. I'm going to pinch in a bit, make my writing look a bit nicer. What are the equations? Well, we've got d2x alpha by d tau squared plus Christoffel alpha mu nu u mu u nu equals 0. So what have we got? That's proper time there. This thing here is Christoffel, and u is the 4 velocity. So what I'm going to do is I'm going to consider an object at rest, because it's nice and easy, at rest. So that says that it's the 4 velocity is ut, ux, uy and uz, 4 velocity, but these components are 0 because it's at rest. So that means that when I do the summation over mu and nu, I can ignore all the components except for the mu equals time and nu equals time. So my, oops, not sure what happened there. So d2x alpha by d tau squared plus Christoffel alpha tt times ut equals 0. See, there are 4 equations here, one for each alpha. So what's the value of ut? Well, we know for any 4 velocity that u dot u equals -1. So that tells me that that equals ut squared times gtt. So that tells me that ut equals the square root of minus 1 over gtt, because they're inverses to one another, which equals, and we've got that up here. We've got that up here somewhere, if I can find it. There it is, it's this thing here, 1 plus c over r. Square root of 1 plus c over r. Have I got 2 squares? No, that's right, that's right. So ut equals that, which is wonderful. So now I can plug that into my equation. I can say d2x alpha by d tau squared plus Christoffel symbol, which I'm still working on, tt, times 1 plus c over r in brackets, just neaten that up a bit, equals 0. So we need to find this thing here. Well, let me show you what I did. I went back to Maxima, which is here, and I got results that I couldn't understand, and I was getting all stressed out about it. The reason being that, again, I've done this several times now, I've got everything correct, and I was looking for a mistake here. I thought I might have a sign error, but the problem is I wrote sine theta there, not sine theta squared. So I'm going to kill this session and start again. Don't save, and fire it up again. Yeah, keep on getting errors. Okay, so we need to load C tensor. There it is. We need to set the coordinates to t, r, theta and phi. There they are. Badly placed commas there. I need to specify the metric tensor with subscripts as a matrix of, now let's see if I can get this right. Oh, just a minute. Where was it? Okay, I'm going to check that, and I'm going to put it into Maxima. Yep. Here we go. LG is the matrix minus 1 plus C over R, 0, 0, 0. Next row, 0. 1 over 1 plus C over R, 0, 0, comma. 0, 0, R squared, 0, comma. 0, 0, 0, R squared, sine theta squared. That was driving me absolutely nuts because I couldn't see the error at all. Let's just check that it is it. Oh no, it's sine theta squared. That's not right. Look, I've closed the bracket wrong. Get rid of that. Put that there. Is that going to be right? Yes. Right. C metric does a whole bunch of calculations under the hood, which is there. Done. Now Christoph. MCS. Boink. Okay. Now, which terms do we want here? Yeah, I got a bit confused there. This this term is the one that we want. The MCS means that we've shuffled around the indices a little bit. So this one here, 2 is the radial component and 1 is time, and it's annoying because I've been using 0. So it's this one I want, which is C over 2R squared plus 2CR. Let me just write that out here. C over 2R squared plus 2CR. Just a minute. That equal to C, lost it, over 2R squared plus 2CR, over 2R squared plus 2CR. And that equals the RTT component. The other ones, the time component is equal to 0. As we saw from here, there's no other match with a 1 there and a 1 there. So the other components are 0. Theta TT equals phi TT equals 0. As it should be. What that's telling us here is that there's no theta dependence. If it starts out at rest with respect to theta, it continues at rest with respect to theta. Theta doesn't change and phi doesn't change. Only R changes in terms of the spatial components. So what we know now is, well, we can just substitute it in. We've got d2x alpha by d tau squared plus c over r, well, take a factor of 2r, 1 plus, no, that's an r, isn't it? Can't factorise, just give me a minute. We're going to take a factor of 2r out, and we've got r plus c there, plus times 1 plus c over r equals 0. So lots of things are going to cancel out here. So that's d2x alpha by d tau squared plus c. I'm going to multiply. I'm going to have an r plus c there. I've got 2 there. I'm going to cancel that one there. I'm going to divide that by r. I've got an r there. That's going to be an r squared. That's an r plus c, and that's going to cancel. Haha. Equals 0. Not particularly edifying cancellation there. Hey ho, but there you go. d2x alpha by d tau squared plus c over 2r squared equals 0. Aha! Now we're getting somewhere. And now I happen to know that the calculation by the inverse square law, we know that c has got to equal minus 2gm, because that's the only way to match the acceleration. The acceleration must be well, we know the Newtonian case. So d2x alpha by d tau squared is equal to minus gm over r squared. And so that tells me directly that c equals minus 2gm. There we go. That's quite nice, isn't it? It took me a little bit of time to do that cancellation there. I thought I was going to lose it there, but there you go. So this constant equals minus 2gm, where g equals 6.671 times 10 to the minus 11 in SI units, and m equals the mass of the black hole. Well, that's nice. Now I'm in a position to write out the Schwarzschild metric in its complete entirety, and I'm going to do that right now. ds squared equals minus 1 minus, remember we have this constant which we know what it is, it's negative 2gm over r dt squared, plus dx squared over the same thing, 1 minus 2gm over r, plus r squared d theta squared, which is kind of boring, plus r squared sine squared theta d phi squared. There it is. And that is a solution to the Einstein field equations. It's a steady, static solution outside a central spherically symmetric object of mass m. And there it is. And this is called the Schwarzschild. Oh no, there's no T in it. Zoom in a bit. Schwarzschild metric. And there it is. And he was the first person who derived this. And I'm going to spend a whole bunch of time talking about this. This is an extremely interesting and profitable and fruitful metric to consider. It's astrophysically realistic. There are real objects that correspond to this metric here, and they have some rather incredible and interesting properties, and I'm going to spend a huge amount of time talking about them. The Schwarzschild metric, there it is. Beautiful. Beautiful. Absolutely beautiful. Stop.